Today we're going to talk about graphing on the complex plane. This is a way of visually showing complex numbers. It's also a way for us to visualize the different operations on complex numbers. So first let's talk about the complex plane. So remember that when we talk about real numbers, you can graph real numbers on a number line. So for complex numbers, because they have both a real component and an imaginary component, we need to account for that imaginary component. And so we can do that by including another axis. So let's say here's your normal real number line. And now in order for us to account for the imaginary component, we are going to include another axis. So this will look similar to, say, your x and y coordinate system. But instead of the x-axis and the y-axis, what we have here is really the real axis and the imaginary axis. And so the real axis represents the real component, the imaginary axis represents the imaginary component. And so if you have some complex number a plus bi, the way you would graph it, it would correspond to the coordinates a, b. So let's take a look at some examples of how to graph these complex numbers. So 5 plus 7i, so this would correspond to 5, 7. So we would go on the real axis, find 5, and then go up on the real axis to find 7i, and that's where our point 5 plus 7i would be. Negative 3 minus 2i, so this would correspond to negative 3, negative 2. So find negative 3 on the real axis, and then go down 2. Now for the next one we have 6i. You can imagine this as having a real component of 0, so this would be the same as 0 plus 6i. And so as a coordinate that would correspond to 0, 6. And for the last one there, negative 2, this only has a real component, does not have an imaginary component. You can imagine this as being the same as negative 2 plus 0i. So that's going to correspond to negative 2, 0. Okay, now let's talk about this term called the modulus. Now the modulus is the distance from a point in the complex plane to the origin. Okay, so simply any point that's on the complex plane, how far away is it from the origin? That's what we call the modulus. Now the way that we represent it is using absolute value signs. Now remember that when we dealt with real numbers, when we had an absolute value sign, what did that mean? That meant the distance from 0. So this is really the same thing, it's just that now instead of having just a real component, it has both a real and possibly an imaginary component for some complex number z. And so when we want to represent how far away is it from the origin, we call it the modulus. It's like the more general version of the absolute value. And so the modulus is represented by absolute value with the number represented on the inside. So here's an example. So say you had some point out here. We'll say it has a real part that's A and an imaginary part that is B. So those are the distances there. Now how would you find the distance that this point is from the origin? Well, since you have A and you have B, we can easily apply the Pythagorean theorem to find this distance here. A plus bi, which is the complex number, and then we put it in absolute value sign. So the absolute value of a plus bi, or the modulus of a plus bi, is equal to the square root of a squared plus b squared. So here's an example. Take negative 3 plus 6i. How far away is that from 0, 0? Well, we have a is equal to negative 3, b is equal to 6. So applying the Pythagorean theorem, we have the square root of negative 3 squared plus 6 squared. Make sure that negative 3 is in parentheses, being squared, so that will end up being a positive 9. So that would be 9 plus 36, which is equal to 45. And we can simplify that. We can take the square root of 9, take that out, so this would be equal to 3 root 5 units. That's how far away this is from 0, 0. Okay, so that can be useful. Now, we have done in the past working with absolute values. If you are trying to find the distance between two numbers on the number line, you can find the absolute value of the difference. And so the same thing applies here. So the modulus of the difference is the distance between two complex numbers on the complex plane. Now, to find the modulus of the difference, the way that you do this is first you find the difference of the two complex numbers. So take the two complex numbers you're trying to find the distance between, subtract them. It doesn't matter which one you subtract from which, because once you find the modulus, everything's going to end up being squared. So after you find the difference, then you find the modulus of that difference. And that tells you how far apart those two complex numbers are on the complex plane. Take a look at example 3. Find the distance between z1 equals 4 plus 3i and z2 equals negative 2 minus 4i. So, like I said before, it really doesn't matter which order that you subtract, because once you've subtracted, you'll end up squaring it when you find the modulus of that number. So for example, here if we did 4 minus negative 2, and then the 3 minus negative 4, we'd end up with a 6 and a 7. And if we did it the other way, you would be doing negative 2 minus 4, which is negative 6, but you'll square it, and then negative 4 minus 3, which is negative 7, but then you'll square it. So either way will work. So I'm just going to do z1 minus z2 here, and then we'll go ahead and distribute that minus to the negative 2 minus 4i. So that would be 4 plus 3i plus 2 plus 4i, and this comes out to be 6 plus 7i. So now we found the difference, and now we found the modulus of that difference. So this would be the square root of 6 squared plus 7 squared. Again, if you did it the other way, it would end up being the square root of negative 6 squared plus negative 7 squared, so you'll end up with the same answer. So 36 plus 49, which is equal to 85. So this is equal to the square root of 85. And that's how far apart those two complex numbers are from each other on the complex plane. Okay, so now we've talked about how do you find the distance between two complex numbers on the complex plane. Now let's talk about the midpoint. So the midpoint of two complex numbers, say these are the two that you have, a1 plus b1i and a2 plus b2i, then the midpoint is given by this. Basically, you're going to find the average of each individual part. So a1 plus a2 divided by 2, and then b1 plus b2 divided by 2. And then the a1 plus a2 divided by 2 gives you the real part, and the b1 plus b2 over 2 gives you the imaginary part. So you'll put the I after the b1 plus b2 over 2. Okay, so take a look at example 4. Find the midpoint between 3 plus 4i and 5 minus 2i. So you take your real parts, so that's 3 and 5, add those together, divide by 2. And then take the imaginary parts, so the 4 plus negative 2, divide that by 2, and that gives you the imaginary part. And then we just simplify this. So 3 plus 5 divided by 2, that's 4. 4 plus negative 2 divided by 2, that's positive 1. So that will be 4 plus 1i, or just 4 plus I. Alright, now let's talk about different operations on complex numbers and how they can be represented in the complex plane. So the first thing we're going to talk about is conjugation. Now, conjugation, what I mean by that is what is the complex number versus its conjugate. So remember that if you had a plus bi, we're talking about a minus bi being its conjugate. So let's say you have a point a plus bi, we'll put it here. Now a minus bi is going to go out the same along the real axis, right? A is still a. But then instead of going up to b, it's going to go down to negative b. So it's going to be down here. So in terms of comparing those two, we can see that conjugation is really a reflection in the real axis. Okay, now let's talk about negation. So negation, so say you have a plus bi, negation would be the exact opposite. So everything is negative. So negative a minus bi. So again, here let's take a plus bi being this point over here. Now negative a minus bi means instead of going out by a to the right, I'm going to go out a to the left. That would be negative a. And then instead of going up to b, I'm going to go down to negative b. So negative a minus bi will be out here. Now comparing these two, you can see that negation is really the same as a reflection over the origin. Okay, let's talk about addition. So say you have a plus bi and c plus di, and you are going to add those together. This one's a little bit trickier, so I'm going to try my best to represent this graphically. Here's a plus bi in blue, and then c plus di I'm going to have in red here. Now I wrote here, use the parallelogram law. What does that mean? So what this means is actually it's up to you. You can either take that red portion that we've just drawn in there and put it at the end of a plus bi, or you can take the a plus bi and you can shift it up until it meets the end of c plus di. Either way, you'll end up in the same location. If you do both, you'll end up drawing out this parallelogram of sorts. So for example, let's say we take the c plus di and I just shift it up over until it meets the end point there for a plus bi. Then the sum of a plus bi and c plus di is wherever the endpoint is for that dotted red line. So that would be there. If you did it in blue, same thing. So if you take the a plus bi portion and you shifted it up and over a little bit to the right until it meets the endpoint of c plus di, then you'll end up at that same location, and now you can see the little parallelogram that has formed. But essentially, where those 2 points are at the end there, that is going to be the sum of a plus bi and c plus di. Lastly, we're going to talk about subtraction. If you are subtracting a plus bi minus c plus di, think of it as the same as adding the negative. So we've talked about negation already, how it is the same as reflecting across the origin. And so we'll use that, and we'll also use what we just talked about for addition. Okay, so here's a plus bi, and here's c plus di. Now if I'm subtracting, now c plus di has been negated. That means I can reflect that over the origin. So reflecting over the origin puts me here in this third quadrant now. So negative parentheses c plus di is there. Now I can add a plus bi and the negation of c plus di. So again, you can draw a little parallelogram if you'd like, or you can just take that negative c plus di, and I'm going to shift it until it is at the endpoint of a plus bi, right there. And now where that newest red point is, that is the result of subtracting a plus bi minus c plus di. So this green part right here, that indicates the difference between the two complex numbers.